Welcome back to Decoding Complexities. I am Pradeep. In our last videos, we explored how to work with individual vectors. We added them, scaled them, and even saw how to measure their similarity. But what happens when we need to handle not just one or two vectors, but a whole collection of them all at once? That's where matrices come in. They are the next essential building block for understanding everything from computer graphics to the architecture of large language models. So, what exactly is a matrix? You can think of a matrix as a stack of vectors or simply a rectangular grid of numbers arranged in rows and columns. For example, this is matrix A, which contains 2 rows and 3 columns. We call it a 2 by 3 matrix. The dimensions are always given as rows by columns. Think of it like a simple spreadsheet. Matrices are incredibly useful because they allow us to organize data. For instance, a matrix could represent an image where each number is the brightness of a pixel, a dataset where rows are different users and columns are their features like age, height, and location. Just like with vectors, we can perform operations on matrices. Let's look at two simplest ones, addition and scalar multiplication. To add two matrices, they must have the exact same dimensions. The process is simple. We just add the corresponding elements together. Let's say we have another 2 by 3 matrix, B. To find A plus B, we just add the elements in the same positions. For example, the element in the first row and first column of A, which is 1, gets added to the element in the first row and first column of B, which is 8. And A plus B will be 1 plus 8, 2 plus 1, and 5 plus 0 in the first row, 3 plus 2, 4 plus 5, and 6 plus 3 in the second row. It's that straightforward. Subtraction works exactly the same way. We would just subtract the corresponding elements. Say A minus B would be 1 minus 8, 2 minus 1, and 5 minus 0 in the first row, 3 minus 2, 4 minus 5, and 6 minus 3 in the second row. Scalar multiplication is also just like it is with vectors. We just take a single number, a scalar, and multiply every single element inside the matrix by it. If we want to calculate 2 times A, we multiply each element from matrix A with 2. That is 2 times 1, 2 times 2, and 2 times 5 in the first row, 2 times 3, 2 times 4, and 2 times 6 in the second row. These basic operations are the foundation for manipulating data in matrix form. As you would expect, NumPy makes working with matrices incredibly easy. We can create a matrix directly by passing a list of lists into np.array method. It's the same method that we have used to create a vector. But we pass the list in order to create a vector. Here, for creating a matrix, we are passing a list of lists. We can also create a matrix by stacking the vectors together. We saw how to create vectors in our last video. Now we will build a matrix by stacking them. Let's define two row vectors, say v1 and v2, and we can use np.vstack method to stack them on top of each other, creating the exact same matrix A. In this case, the vector v1 would be the first row of the resultant matrix, and the vector v2 would be the second row of the resultant matrix. Similarly, if we have a vectors and we want them to be the columns of your matrix, we can use np.column_stack to place them side by side. Let's say we create two column vectors, c1 and c2, and we pass c1 and c2 as arguments to np.column_stack method. And the resultant matrix would contain c1 as the first column and c2 as the second column. Now let's see how easy addition and scalar multiplication are. So let's recreate our matrices A and B, and we simply use the plus operator for doing the matrix addition, which is A plus B. And for scalar multiplication, we multiply 2 with matrix A. NumPy handles all the element-wise operations for us, making the code clean and readable. So We can organize vectors into matrices and do simple math with them. But the real magic happens when we multiply one matrix by another matrix. Matrix multiplication isn't as simple as element-wise multiplication, but it's the core operation that allows us to do incredible things like rotating 3D objects in a video game, transforming data, and power the calculations in every layer of a neural network. If this was helpful, please hit the like button and subscribe so you don't miss our next video where we will deep dive into the mechanics of matrix multiplication. Thanks for watching.